So what I want to look at is this worked example for estimating gas production rates. And this example is really nice to work through yourself. Because it gives you have to go through all of the steps of what the model would be doing in Eclipse 100 with doing the GPP calculation. And we're using a model here that doesn't have the GPP calculation in it, but we can go through the whole calculation procedure. So this is a worked example to demonstrate the use of the gas condensate rate equation to estimate well productivity, taking into account condensate blockage. That data is taken from a sensor simulation model to allow comparison with simulation results. This is a lean condensate reservoir, 1,000 millirc feet, so we know it's going to have blockage is going to be important. This is the wellbore radius, 1/3 of a foot, RE 3,000 feet, mechanical skin 0, average reservoir pressure 4,000 pounds. I think that's maybe equal to the dew point if I remember right. Wellbore flowing pressure 1,500 pounds. Lean condensate, similar to what we were looking at for Kuth formation. Here we're using rock relative permeability curves with a Corey exponent of 3. Assuming an oil saturation of 1% outside the near well region 2. These conditions correspond to the sensor simulation case after 3 years of production. And what you can do is you can reproduce all these calculations in Excel that he's doing. The output file is actually in this E node here. Go to the E node, gas condensate rate, and you see this output file. That's all you need. Okay, it's a sensor output file. So you can find all the numbers needed to do the calculations in his Excel sheet at 3 years. Well, you can go and redo that at 2 years or 5 years. You can pick your own numbers out and redo the calculation at a different time. In addition to doing it at 3 years, because then you can check your results that you understand how it's being done. Okay, so the rock so that's the data set I just opened. Okay. Oh yeah, not sure the rel-perm rock curves are. Let's see here.
It also says slide number something. Corey functions like
radial 2. What's that?
On the PowerPoint it says slide 4, rock relative permeability exponent of 3, data on slide 4.
That's here. Okay, there it is. Yeah, so that's here. I think in the Excel sheet. So statement problem is estimate the maximum gas production rate for the well. Estimate the condensate blockage skin. Here's the rel-perm. I'm not sure why it's not plotted as KRG versus KGKO. It should be somewhere plotted that way. That would be the first thing I would do is take that. You can see the crossing point is at about 0.08, it looks like, which is in reasonable range. These are the Blackwell PVT properties. Dew point pressure of the fluid is 3734. Let's see, the RS and BO, are they monotonic or not? 156, 59, 5965, yeah. So the BO is monotonic barely, and the RS is monotonic. So step 1, estimate, as we did yesterday, the KGKO ratio, flowing OGR, and all other PVT properties. This is exactly what we did yesterday.
How did RP? How did you get
That's
RP?
taken from the model at 3 years.
Oh,
So it's
okay.
the true,
Makes sense.
yeah, this is all perfect data. So this is the model producing oil gas ratio at, we can check that at, from the data set. Let's see, where would that be? Maybe at the end here. Okay, so we've got, these are summaries. So GOR at 1,095. That's 38,461. Can you do the inverse of that times a million? That would be the
1 divided by 38,461. 26.
26 barrels per million. Okay, comes straight from the producing oil gas ratio. And then the tubing, the Blackwell table, he's got that here at 20. What was it? 21 or 26? So 26 is interpolated somewhere here between 3,500 and 4,000 dew point. And he says that it interpolates to 3734 by interpolation. So that would be our P star, region 1 P star boundary. Above the dew point, KRO0. So this is exactly the calculation we did yesterday and made the plot. Okay, here's the plot of KRG versus KGKO. Okay, you can see the crossing point, 0.08. And then basically he goes from minimum bottom hole flowing pressure of 1,500 pounds up to the P star. He calculates the KRG, KRO, and then he did what we didn't do yesterday. He went ahead and interpolated into the rel perm curve. Or maybe he drew an equation, he got an equation through this and then calculates the KRG for each of these. And that's shown here. And you can see how pretty flat it is throughout the region 1. Around 0.2. Of course, at the dew point, there's no liquid, so KRG should be initial KRG. Then we're going to calculate this mobility, units, mobility, you got to be careful on units there as well.
So there is no region 3 here, right?
There's no region 3 here, it looks like. Yeah. So we have to calculate this term here. And in this, for all these pressures here, we had the KGKO, we had the KRG, that gives us the KRO. So we've got all of those. We got the PVT properties as we had last. So basically we can get all these numbers. That gives us the gas mobility. The second term is very small, can be neglected, it's less than 1% for the example. And then basically from the trend of mobility here, he just extrapolates out to the dew point, okay? Now obviously the true function will go as a smooth function dropping like a rock and then kind of blowing in the wind to the west, and it'll end up over here. But he just approximates that as an extrapolated straight line. And if it would have stayed single phase, then this function here would have been going something like this. It would probably start turning around a little bit, going down towards 0, 0 over here. But you definitely have lost a good chunk of your area. Calculates by just simply adding these delta P times the gas mobility to get the area, trapezoid rule. gives a flow rate of 21.3 million standard cubic feet per day, and from sensor 21.5. So it's not very far off.
I think is that it, or
What's that?
do we have more? Because I'm thinking another good exercise here would be that if you assume that your RP is equal to RS,
Then you could do, yeah.
and you can see how much different results you can get.
Exactly. Yeah.
If you didn't have the reservoir model.
Yeah. Basically, you'd lose this area here, which is 20%, about, by eye. Yeah. 15-20% of the total area, maybe more. It's not a very big area here. Maybe 20-30%. Lower rate than 21.3. So that would be like around 15 million instead of 21 million. Just because of that little difference. So condensate blockage. So here what you can do is recalculate the mobility, assuming that KRG doesn't change. You just use the initial KRG. Calculate the pseudopressure integral. You get 90,000 area instead of 25,000 area. And basically the productivity index would have to change to represent this. And the condensate blockage, when you calculate this way, would have to be a value of 22. And then the spreadsheet with all these calculations is given here. Then he's got some questions here. How can we include the effect of velocity dependent rail perps? We haven't really talked too much about that, so let's come back to that again later. But this is I think it's just a great example that you can actually go through and make the calculations, compare it with the simulator, and prove to yourself. And clearly, if you just use zero skin, ignored it, you're going to get way too much rate. Probably 3 times as much rate as you should.
And if you do this calculation for like future years, like this is for 3 years, then if you do that for 5 years, 10 years, then you will see that the skin will be dropping.
Will be dropping, yeah. That's right. Because as you get the producing gas oil ratio increases, these numbers are all going to increase, and these numbers are also going to increase. The PVT properties don't change. So that this thing will be lifted continuously upwards. It won't be lifted to 1, but it'll become higher and higher. That's right. Okay, so this is a good point to discuss about the velocity dependence of capillary number dependence relative permeability.
Curtis, I have a question.
Are these calculations in this calculate gas rate using rate equation Excel sheet?
Yeah.
Or
here? Yeah, it's called calculate gas rate using. I can open it up here.
Maybe you can very briefly go over the Excel sheet and
Okay. Okay. Yeah, the rail perm sheet here, I think is being calculated. This is probably the SR, the analytical. These are the same as we looked at yesterday. Kind of the same thing we did yesterday with the KGKO. Here, PVT table. He's using some kind of interpolation, I think, to get these numbers. Yeah, so exactly what we did yesterday to get the KGKO ratio, and then to get the KRG by interpolation from this. PWF, reservoir pressure, area. This is with the KRG effect. This is without the KRG effect. No blockage. Using a KRG of 0.96. You got the mobilities here and here. Gas rate. He's got the 2 pi conversion factor, just exactly. He uses cell names a lot instead of cell, so he actually names cells to make it a little bit easier so Cage can see a little better what the equation is.
so what is this table? Second table we used to plot chart.
Table. I'm not sure why he had a separate table for plotting. I'm not sure. It looks like the saturation numbers are identical. Okay, he's got some kind of if statement. If it's less than C19, so KRG is changing. Not sure. It doesn't seem to. I'm not sure why it doesn't just plot the original table. It doesn't look like it has any different numbers in it. Okay, here it is.
Yeah, it's for just for the plotting of these high separation.
Oh, okay.
So
And the gas saturation, it stops at the 1 minus water. This is the KGKO that was in the table here. 7.2. Yeah, it starts at 3,500, 42.5. Yeah, so it's just these numbers here. That's exactly what we calculated yesterday, the KGKO. Same equation, Blackwell tables. And then he does something on indexing to get the interpolation to the KRG. So this is by interpolation in the I don't know where the plot is, Relperm, but no, this one here. So he's got he's doing interpolation to get the KRG from the KGKO here somewhere. This one here is basically just using interpolation. And you get the KRG, and the KRO is just simply KRG divided by the ratio. That's used in the mobility. You can see here, KRG divided by KGKO, mu OBO, RS. So that's the second part of the lambda term. So totals, these are the total 4.3. Not sure why we're not getting the same. Okay, total is 10 here. This one here, the sum of these two. Sum of these two are about 7.6. So I'm not sure, he didn't seem to sum them, but that basically is the sum. 750, it's 2.6 plus almost nothing.
Okay, here, because here in the presentation he stated that lambda O will be neglected.
Yeah.
So it's only lambda G.
Yeah. So at 1,500 pounds, he went to 4.2, 4.3. Yeah. So these are all the same numbers coming out of these calculations here. So I think it just takes a little bit of detective work to figure out how all of the numbers are coming up, and then you'd have to change those for a new time and a new little RP. But okay. Okay. Any other questions or comments about this example?
Curtis, I had a question. When we were discussing this, like implementing it in MBEL or something. So one way is to have this tubing head tables.
Right.
You can have tubing head table, but if you want to calculate, if you want to include tubing head tables, so the extra pressure drop that you will calculate and you will add to this pressure drop, that extra pressure drop will also assume that your P star is equal to PDU, right? You will not have this region 2, and that will also give you less deliverability. Like if you don't have a reservoir model and if you just have like MBEL or Prosper.
Yeah, so what you have is, if you're going to build a table, you're going to build a table that goes you have you can have a pressure node. You'll have a node for OGR, producing oil gas ratio, that you know. Okay, and then you'll have some PWF minimum, 15 psi, whatever you want. Okay. This will immediately give you P star, right? And and then you'll, using this procedure that we just looked at, this will give you the let's see here, you have the rates given, right? So the rates given. So if you just set up a table here to P star, your C's known constant, okay? That's always going to be the same. So what you can do, you can calculate at each of these pressures. You can get the KRG, KRO. You get the KRG, the KRO. You get the mobility of gas total. And then you would get gas rate. Let's see here. There. Okay, you're not using rate anywhere here. In M value, you would also have average reservoir pressure, right? Yeah. So out here, if that's greater than P star, then you're going to have potentially, so this would be your region 2, this would be your region 3, and all of this would be region 1, right?
But first, in EMBA, like we are assuming RP is equal to RS, so there is no region 2.
Yeah, then region 2 would disappear, but I was just thinking that if you have a general tubing table, how you would build that. I think you know, for a given RP, you get immediately the P star, and then you can go out to any other higher pressure. So you can kind of so I think that if you just build this lambda, and then you build the area, this area of the gas here, which is just, it's like building a pseudo pressure function for gas. So you just add up, you know, your sum of delta P like that, right? All the way up. Then you would have the area here. And then basically you've got this QG is equal to C, that's known, and area G, which is a function only of PWF and PR. All right. And that's like inflow and outflow of the tubing. So you basically have to, if you specify, if your pressure nodes are then going to be, so you can, it's exactly how you'd construct it, I'm not sure, but it's got to be like a tubing table. Basically, you have inflow, outflow pressure, and QG, and yeah. So you build the table some way out of this. But certainly for any RP, you immediately know this, and you have a minimum pressure, so you know that where you start from. So you start here, you go to there, and then you can go beyond that single phase as far as you want, and get your tubing, so. And like you say, if RP is equal to little rs, then the P star is going to be equal to dew point. You would still be able to use this. You get the single phase region and the two phase region throughout. So I think this is how you'd want to construct it to make the table.